All right, I got the recorder started and just need to share the screen. Yeah, this one is fine. All right. So I hope you guys got an opportunity to kind of catch up with the material of this class because um, the progress for the last few classes is going to be, I would say, a little bit on the fast side for people who may not have a good foundation. But as long as you guys clear away all the concepts that we have talked about before, I don't think it's going to be an issue. So let's go back to this class. I did some changes, additions to a module that is already linked before. But that's okay because I'm not changing what I have already talked about. I'm changing and adding some content related to what we will be talking about. So it is the caller-callee agreement document that I revised just a little bit. Let me show you what it looks like now. It looks about the same as before, except I put in a big header section header of mutual agreement. In other words, everything in section 1 is something that needs to be known by the caller as well as the callee. And then section 2 only talks about something that only needs to be known by the callee or the function being called. And then section 3 is a suggestion of how to structure the way we look at how the stack is used. So not a whole lot has changed. What we'll be talking about today is how do we deal with arguments on the caller side, and on the callee side, how do we handle parameters? Basically, the same thing, except the terms are different depending on which side you're talking about. So from the caller's perspective, if there are arguments, the arguments are pushed in reverse order, which means the last argument is pushed first, which also means it ends up with the highest address compared to the other arguments. Um, and in TTP, arguments are pushed contiguously. So what that means is we do not leave any empty space behind. We do not leave some byte locations unused. So everything is just contiguous. On a 64-bit platform or on a 32-bit platform or even on the 16-bit platform, sometimes we intentionally leave some gaps to minimize the number of memory cycles that we need to use in order to access the parameters. The rest is pretty much the same. And the only other thing that is related to arguments is down here. If there are arguments, the caller is responsible to clean up the stack space used by the arguments. So that's the only thing we also have to pay attention to in today's lecture. On the callee side, the function being called, at the entry point of the callee, the stack pointer is still being pointed to by the stack pointer points to the return address because that's still the last thing that we push on the stack. But if there are parameters, the parameter would be, in terms of memory location, it would be after the return address. The first parameter starts at the address that is immediately after, in parentheses higher than, that of the return address. Okay, so this is basically a consequence of how the caller push all the various items onto the stack. And I think the last portion here, which is kind of in the form of a table, that could be helpful because this kind of shows us how things are organized. If there are indeed arguments, the arguments would occupy the highest portion in terms of address space, in what we call a call frame. So this is a frame of calling a subroutine. The arguments would be at the highest portion. The return address is the last thing that the caller push on the stack. So the stack pointer points here at the entry point of the callee. If there are local variables, the local variables would be below the return address. We're not going to get into local variables today, so we'll be focused on just arguments. All right, so do we have any questions about what I have talked about so far? Any questions about the concept of the stack? How we grow the stack from high addresses down to low addresses? No questions about those? Okay, excellent. So what we'll do is instead of reading, because I could, just do that too. So if I want to point out which part of the lecture we are talking about, it would be parameters and local variables. So I could just read the module, but that's going to be super boring, at least to me. And also it's going to be a little bit boring for people who read the material ahead of the class. So what I would do instead is I would show you sample programs, and then we'll work out the sample programs while I will be explaining the concepts at the same time. So that's going to be the format of today's class, and I suspect it's going to be the format of quite a few classes that we'll be having until the end of the semester. All right, so let's go ahead and take a look at a relatively simple program. We'll call this one, I did subtraction already. I'm not sure I want to do subtraction again. We'll go ahead and do subtraction again, but this time it is unsigned subtraction. So we'll just call this unsigned subtraction.c, and we'll also work on the unsigned subtraction TTP ASM at the same time. All right, so we'll work on the C code first. The C code is going to start with pound include stdint.h, and that is something that we learned when we talk about the double conversion. It's standard integer.h, which allows me to specify types like this. And this is a subroutine, with a name of usub, because it's unsigned subtraction. And really, it doesn't matter. I mean, you guys already know that subtraction is going to be exactly the same whether we are dealing with signed versus unsigned. So it really doesn't matter one way or another. And then the main program or the main subroutine, the main function, does not do anything other than just to call usub, and we'll specify, 45 as one and then 23 as the other one. Return 0. So that's the C program. Do we have any questions about the C program itself? Because if there were, I'm going to send those people back to CISP310. All right, so working on the assembly code. Okay, so on the assembly side, we have a no op, okay, because it's needed in order to trace the code, JMPI to main, so that we go around the definition of usub. And in usub, I know it's a subroutine, so I might as well just include the 3 instructions to return to the caller. So the 3 instructions to return to the caller is LD, BD. I cannot use A because the subroutine returns a scalar, which means register A is going to be used to specify a return value. I cannot use register A at the end of the subroutine. Increment D, and then JMP, JMP-B, there we go. And now we can start with main. The first thing main needs to do is to initialize the stack pointer. So LDID0 would do that. The last thing it needs to do is a halt instruction. So everything we need to do is going to be between those. All right, so I got a shell of the entire program ready. And then the first thing we need to do now is to call usub with 45 as my first argument and 23 as my second argument. The first thing we need to do is to push 23 on the stack. In some architecture, this is all you need to do, is to say push using a $sign to indicate this is an immediate operand, 23. Can't do that with TTP, okay? Because TTP does not have instructions like that. So what we need to do is kind of a little bit cumbersome. Decrement D, LDI, we can use register A. We can use whatever register other than D. 23, STDA. So that's going to push the value of 23 on the stack. So at this point of time, I think it is important for all of us to be able to recognize these 3 instructions is just pushing 23 on the stack. It is important to understand, to do the conversion both ways. If I say I want to push 23, you need to almost immediately be able to come up with these 3 instructions. And when you see these 3 instructions, it'll be very helpful to immediately recognize that we are pushing 23 on the stack. That would be tremendously useful for the final exam. And the only way to get there is to get familiarized with the code, is to kind of read it, document it, and try to understand the code as much as you can. All right, so that's my second argument because we have to push the last argument first. So that means now it's time to push the 45. Kind of the same code, decrement D, LDI. We can use B if we want to, doesn't matter. And then STDB this time. And then we have to push the return address. So we push all the arguments first, and the last thing we push from the perspective of the caller is the return address. So now we need to push the return address. And I'm going to try something new this time, okay? I'm not sure whether I have introduced this in this class or not, but this is how I'm going to push the return address. Have I done this before in this class? I don't think so. Okay, I'll explain that, okay? So register C actually contains the return address at this point, but I still need the other instructions to actually put it to the location that I have just allocated, and then the JMPI instruction to the subroutine, which is called uSub. And when we return from the subroutine, we need to increment the stack pointer because we still have the two operands, the two arguments sitting on the stack. So we need to increment D twice to quote unquote move the stack pointer past the two arguments that are still sitting on the stack. Oh, this does not belong here. This belongs all the way up here. All right. So I think that should do it from the caller's perspective. So before I move on to talk about the callee or the function being called, we'll just quickly go over this and say this is push 23, this is push 45, this is push the return address, and this allows me to continue execution at the subroutine. All right, so before I move to the callee, let me explain, okay, let me turn on the line number so it's easy to see. So let me explain line 18, what it is doing. So the key is, what is the dot notation? The dot notation is saying it is the address of the instruction that is on the same line as the dot. Okay. So in this case, this dot here is basically the address of the LDI instruction. And we already know the assembler takes postfix notation when it comes to expressing a calculation. Instead of an infix notation, which is dot plus 5, it uses a postfix notation, which is now dot 5 plus. Give me the address of the instruction, give me 5, and then now I'm going to add the two items that it was given with. So why add 5 to it? The LDI instruction takes 2 bytes. So we have offset 0, offset 1. ST is going to take 1 byte, so this is offset 2. The JMPI instructions take 2 bytes too, which is offset 3 and offset 4. So by the time we get to offset 5, it is the increment D instruction, which is exactly where the subroutine is supposed to go back to. So that is why I can use dot 5 plus on the LDI instruction based on these instructions to specify the address of the increment D instruction. Do we have any questions about that notation or any clarification that you want me to do? No questions? Okay. I can show you exactly how the assembler assembled this. Okay, so we can actually take a look, from that perspective as well. So assuming there are no immediate questions about line 18 at this point, we're going to move on to uSub here. And what I personally find helpful is it is good to draw a picture of what the stack looks like at the entry point of uSub. So I can expect parameter y, I can expect parameter x on the stack in that particular order. Y has a high address, x is the next highest address, and then we have the return address here. And that is being pointed to by register D, which is our stack pointer. This is what the stack looks like, or what the subroutine can assume when we get to the entry point of uSub. So the question now is, how do I get to X and how do I get to Y? And a way to do that is to say, well, if I add 1 to register D, that should become the address of X. But I don't want to do that because I don't want to change register D, especially going up, because if I increase register D, I'm changing the border, the line that is between the portion of the stack that is in use, and it is protected from the gremlins, and also the portion of the stack that is not supposed to be in use, and the gremlins can play with that portion of the stack any way they want to. So I don't want to increase the stack pointer. But that's okay. We got a few other registers. So why don't I copy the register D to another register? I can copy the register C like that, okay? So when I write code to do this, I personally would comment each and every single line so that I can understand the context of that instruction. Why am I doing this? How does this relate to the stack? And on top of that, how does that relate to the C concept or the C++ concepts? So in this case, C basically becomes the address of the return address on the stack. So are we doing okay so far with that comment? Okay. Well, that's okay. That's nice because now I can say increment C because I don't have to mess around with register D anymore because register C is based on register D, and I can increment, decrement register C all I want, and because it's not the stack pointer, it's not going to change the border or the boundary of which part of the stack is protected and which part of the stack is not protected. Question?
So D is like making the kind of delineating how big the stack itself is, or how many values you were using in the stack, and
Yep.
then C in this case would be like the index, right?
C can float around. C is just a pointer to somewhere.
Yeah, and in this case, would it be like the index we're using?
Yep. So C is how we can get around to get to the parameters. So by incrementing C, so in this picture here, C would be pointing to X. So register C now is going to be the address of X. Not X, but the address of. Okay, now that is really important because register C is still pointing to something on the stack, the portion of the stack that is being used, but register C itself is not the parameter. The parameter refers to the value at that location, so we have to be careful and make sure that we understand this is just the address of parameter X. But once we get to the address of parameter X, it's easy to get to the value of X. So can someone tell me which instruction I need to use to get to the value of X? There's only one instruction we can use, which is, what is the opposite of store?
Load.
Load, that's right. Okay, so we have a load LD, not load immediate. So in this case, I can use register A or register B. I'm going to pick register A for a specific reason, but that reason will be clear later on. Okay, so once I do the load, register A would have the value of parameter X, which is great. Okay, it's one of the two things I need to do the subtraction. And then I can increment C one more time. Oh, I said C. So C is now the address of Y. The reason why this is the case is because Y is living 1 byte on top of X. In other words, the address of Y is 1 plus the address of X. Is that part okay? Because this is really crucial, okay? Because this is kind of the essence of today's lecture right here. I'm just using multiple example programs to illustrate the same point, but this is the important part. Is that okay? All right. So now I can use register B, or I can use, okay, well, I don't really need to keep track of the address anymore, so I can now say register C is the value of Y at this point. So the only thing I have to do in order to, because I got the value of X already, I got the value of Y, so all I need to do is to do the subtraction, but I got the values, the minuend and the subtrahend in the right registers already, because the result is supposed to be X minus Y, and register A is supposed to hold the return value, and everything is already in place. All I need is subtract C from A, and register A will then become the actual return value. The rest of the 3 lines, 14 all the way to 16, that's just the usual return, instructions. So I'm all done. Are we good so far? All right. So are you guys just gonna take my words for it? Of course not, right? We want to like it run. Okay. Got to make sure everything works correctly. All right. So that's what we're gonna do next. And I'm just gonna pick out. Or I can get out of this one. And then we can use River Spider to submit use sub.ttp-asm. All right. So if you have not set up to use River Spider, you probably need to kind of practice a lot to do the same thing manually, because you will get programming assignments at some point, and in that case, being able to trace the code and analyze your program is going to be quite important. All right, so this is all done, and I can now go back to the assembler. And I talked about this already in this class. I added column F that shows the line number, and also column G that shows the actual source code of that line. So that makes it much easier for you guys to kind of follow along. It's like, okay, where are we in this code? Yep, we know exactly where we are and what it's supposed to be doing. So in this case, let's track it down. Okay, so I'm going to track down the code here, and I can see some of you are already viewing the same document. I would make a snapshot. Okay, if I were you, okay, if I were a student, I would go to File and say make a copy, and then stash that copy away someplace and name it appropriately so that you can refer to that particular Google Sheet for reference. All right, so I'm just going to quickly go through the instructions, how it executed. No op, doesn't need to explain that. I don't need to explain that. JMPI to main, this is to go around the definition of the subroutine. Inside main, the first thing I do is to initialize the stack pointer to 0, and that's the result. And then I push 23 on the stack, which starts with decrementing D to move the boundary of the stack, which part is in use, which part is not. I move that boundary by 1 byte. In other words, I reserve the location first. And then I put 23 into register A, because that's the only way I can store something into RAM, is to have a register to specify what I'm supposed to be storing. So we can also see the stda is changing location FF to the content of 17. 17 is 16 plus 7, which is 23. Are we good so far? Okay. So moving on, the next 3 instructions is pushing 45 on the stack. So here we have 45. Oh, here we decrement D again. So D is now FE in hexadecimal. We load 45 into register B. So register B now is 2D in hexadecimal, which also makes sense because 2 times 16 is 32. 32 plus 13 is 45. So 2D is 45, or 2D in hexadecimal is 45 in decimal. I store that to wherever D is pointing to. So now location FE is getting the content of 2D. And then we push the return address. So this is decrement D again. So D becomes FD. This is the kind of magical thing that I explained, or I tried to explain earlier, which is this is how we specify the return address. So to explain this one, the best way is to look at the Assemble tab. So we can go to the Assemble tab and go to this kind of mysterious instruction, which is on row 18. So on row 18, we can see that the opcode is 6E. Okay, the 6E part is pretty easy to explain because it has to do with the opcode format. But we can see the second byte is 16. 16 is specifying the return address. And the return address is supposed to be the first increment D instruction, which indeed is at location 16. On the other hand, you can also say, okay, if the LDI instruction is at location 11, and that's what the dot is representing. The dot is representing where is the instruction, and the instruction is at location 11. And if we add 5 to it, 11 becomes 16, and that's how we ended up with 16. So is that okay? Does everybody understand how .5 plus works? And why would I want to do something like this instead of using labels?
Saves lines of code.
Hmm?
It
saves lines of code?
It saves one line of label definition, but it doesn't really save anything at runtime because labels do not exist at runtime. So it doesn't save you anything execution time or code otherwise at runtime. What it does save you are potential issues, because if you use labels, you can refer to the wrong label, and as long as that wrong label is defined, the assembler cannot catch that problem. So it can be branching to the wrong place, or when you return, it will return to the wrong place. So, but with this approach, it won't do that, okay? With this approach, when you need to call something from row 17 all the way to row 20, these four can be used anywhere you want, okay, to call any subroutine, because you don't need a special label to define where the subroutine is supposed to go back to. Alrighty, cool. So now we go back to the analysis tab. Yep.
Let's say you want to add like a line of code between that LD instruction.
Then you have to make some adjustment, yes. So you have to be careful because the 5 is sensitive to the actual number of bytes between where the LDI instruction is and where you want it to return to.
So if you added something else, it'll just like make nonsense.
Or, well, it depends on what you want to do. There are tricky things you can do in this case. So some of the tricky things you can do is to specify this 5 to be more than 5. Then you can stash some data items over here that is going to be skipped over by in terms of execution. But that's really tricky stuff. I would not recommend people doing that. But you can do fun stuff with it. Okay. The other thing is if you reverse these two instructions, they can be reversed because one only affects register C, the other one affects register D. So they really do not need to be in any particular order. But if you flip the order, the 5 needs to be changed to 6, because then you have 6 bytes between the LDI instruction and where you're supposed to return to. So you got to be careful with that. All right, so getting back to the analysis tab. So now we push the return address, which is 16 on the stack, and this is how we overwrote that location on the stack. Then we continue execution at usub, starting at location 3. And what it did was to copy what is going on here. This is LDBD. That doesn't make sense, does it? LDBD. At location 3. Did I make a mistake somewhere? Oh, I know what I did. Okay, so this program is not doing a single thing because it's returning right away. And that's because I forgot to save the file before I ran River Spider. Favorite mistake of myself, okay? You can see this little plus here. That little plus means the file has been modified. I did not save it. I forgot to save it first. Okay. That explains that. It's because I was looking at the code and go like, no, that is not what it's supposed to do. It's supposed to do a CPR CD. All right, so let me rerun the whole thing. And this is why it's nice to use River Spider, because I just press the up arrow key, press enter, and that's refreshed the entire thing. So now, when we go back to the analysis tab, this time, we have CPR CD. Great. Okay. So register C is now a copy of register D, which I said would be pointing to the return address. And you can see how FD is 1C, which is the return address. I increment by 1, then register C becomes the address of parameter X. Parameter X is supposed to be the 45, and you can see how FE was last updated to have the value of 2D. I then load the 2D into register A using the LD instruction. So register A is now 2D, which is the 45. And then I increment register C again. It is now FF, which is the address of parameter Y. Parameter Y is supposed to be 23, and that's how we got the value from that location into register C itself. So, to understand how it was able to, okay, I just dragged something when I'm not supposed to. So to understand why register C updated to 17, all we have to do is to go back earlier, and then we can see how how the location FF was overwritten by 17. That is the 17 that we retrieved later on into register C. And then we perform the subtraction. So we have 2D minus 17, which ends up as A, 16, and it is stored in register A. And that's the end of the calculation. And then we retrieve the return address. The stack pointer is now pointing to the return address. So that return address 1C is put into register B. We increment D because the return address is supposed to be popped by the subroutine being called. So D is incremented from FD to FE, and then we perform a JMP-B instruction to go back to the caller to continue execution at 1C. Location 1C has one increment instruction. The increment D instruction increments the stack pointer from FE back to FF. Another increment D increments the stack pointer from FF to 0, 0, and then we get to the halt instruction. The stack is balanced. Register A has the correct result of 16 in hexadecimal, which is 16 plus 6, which is 22 in decimal, which is the correct result. So that kind of shows how the program works. All right, do we have any questions about this? No questions? All right. All right, so now we can actually start to do something a little bit more fun, okay? We can try to compute the square of things, but without using multiplication, okay? Because I did power of 2 in the other class, I just kind of feel bored to do exactly the same thing again, so I'm going to do something a little bit different this time. All right, so we'll go to a mouse pad so I can explain the math first. Once the math is explained, then I can go ahead and explain, the actual subroutine. All right, so the idea of computing the squared of something, but not using multiplication, is to take a look at what x plus 1 squared is supposed to look like, okay? It is x squared plus 2x plus 1. I mean, you guys know this already. This is pretty elementary stuff. But if I keep track of x squared, then it becomes just whatever x squared is plus 2x plus 1. So to get to x plus 1 squared, okay, so if I were to say f of x is to compute x squared, one way to do this, okay, is to define f of x to be 0, okay? I should be saying define f of 0 to be 0, okay? That seems to make sense. But then for everything else, okay, we define f of n to be f of n minus 1. Okay, now I need to change this to a, okay. I think it is plus 2x minus 1, okay? So it's a recursive definition, but it only involves addition and subtraction and not multiplication. And someone's going to say, but Jack, isn't this a multiplication? Fine. Happier now? Okay, let's check whether this works or not, okay? Because, I'm still having a little bit of a mental picture of, I'm not really sure. Okay, so let's compute f of 1. So f of 1 is f of 0 plus 1 minus 1. Great. And f of 0 turns out to be just 0. So we have 0 plus 1 minus 1, which indeed is 1. 1 squared is 1. Okay, let's check 2. Just double check. So f of 2 is f of 1 plus 2 plus 2 minus 1. And f of 1 is 1. So it becomes 1 plus 2 minus 1, which is 4. Okay, I'm sufficiently convinced that it works. Okay, and if you guys are thinking, but Tech, that is hardly any rigorous proof, um, I would agree. Okay, this is not a mathematical proof, but it is not CISP310 that is supposed to teach you how to prove by induction. That is supposed to be CISP 440. So if you have taken 440 already, this would be a good exercise to see whether you still understand what is proof by induction, because it's actually a pretty easy thing to do. Okay, proof by induction is one of those fun things where if you look at it, it looks kind of complicated, but once you practice and understand how the way it works, it's like, wow, that is powerful and it's easy. Okay, if you have not taken CISP 440, you can leave a note to yourself and go like, okay, when I take CISP 440, I want to be able to solve this one. I want to be able to prove that if I define f of x recursively in this way, it is actually just computing the square of x. Okay? But that's all I'm going to say for now, okay? Because the focus of this class is not proof by induction, but instead I'm using this as an opportunity to show you how to push arguments on the stack, how to access arguments, parameters on the stack. All right, so I'm going to stash this on one side while I write the actual code for this thing here. All right, so let me go back to this slide because I don't need this one anymore. So I can say XA to exit and save all. And this time we'll work with square, sqr.c and sqr.ttpasm. We'll work with the assembly code, the C version first. So once again, pound include std int.h, uint 8 underscore t. So I'm only returning a unsigned value on as the return value. And this is the square of an unsigned integer of n. And I would use a single return statement to do this. So this is return if n equals to 0, we'll return 0. Otherwise, we will return f of n minus 1 plus n minus 1. There we go. That's the recursive call. So do we have any questions right now just with the C code kind of encoding what the f of n is on the other side? In other words, are there any questions about how this is implementing this part here? Other than I just used the wrong variable here. Other than that, are we good so far? All right. And obviously, I also referenced the wrong function name because it's not f. It's supposed to be sqr over here. And then main is going to call that thing. So we have sqr of, I think we can do up to maybe 4 or 5. Okay, we can do up to 4. Return 0. Okay. So the C code should compile, okay, unless I make another stupid mistake somewhere. It should compile, and you can actually test run it to make sure that it does what it's supposed to do, which is computing the square, but using a recursive definition. On the other side, we are now working on TTPASM, the usual template like that. And then we define SQR as a function, LDBD, increment D, JMPB. Okay, that's just a shell of a function. I'm not implementing the logic of it yet. And here's main, initialize the stack pointer, do a halt, and now I can insert the code in between. So this time it's not too difficult to deal with because I only have to push 4 on the stack. So that's going to be decrement D, LDIA with 4, store DA, and then we have to push the return address this time. So decrement D again, LDI A dot 5 plus, STDA. Now we can continue execution in the subroutine, which is SQR. And then when it returns, we have to increment D just once because we have only one single argument that is still sitting on the stack at this point. The increment D will quote unquote deallocate from the stack so that by the time we get to the halt instruction, the stack pointer should be back to 0.
I think
Question?
we have a number of increment D instructions equal to the amount of parameters we have, right?
Yes. So the decrement D here is balanced by this increment D, but the other decrement D is not balanced by the caller because it's the callee's responsibility to get rid of it. So if you include the callee, then we have the right numbers of increment versus decrements. Yep. All right, so from the callee's perspective, now we need to figure out what to do. Okay, so when you're trying to compile a program into assembly code, you kind of have to think about the ordering of what you need to do. So when you look at the only line inside square, what you need to do is to figure out whether n is 0 or not first. So that is going to determine how you write your code in the subroutine as you translate C code into assembly code. All right, so we're going to do LDI. No, I used the same approach as before. Okay, CPR CD. So now C is the address of the return address. And then we increment D just once. C is, whoops, increment C. So the C is now the address of N. And I'm just looking at this and go like, hmm, hmm, hmm. Okay. I just have a few things that I need to think ahead of time, but I think right now we can just do a LDCC, okay, like so. So the C is actually the value of parameter n. I don't need anything else for now, okay, so we'll just go ahead and do it this way. And we need to see whether n as a parameter is 0 or not. And we learned this trick in one of the labs, okay? Because when we push a register through the ALU, it's going to affect the Z flag, which in return is going to tell me whether the register is 0 or not. So ANCC is forcing register C through the ALU and setting the Z flag as well as the S flag accordingly. And now I can just do a JZI to see whether it is actually 0 or not. So if it is indeed 0, I can go to a subroutine. And in that case, we're supposed to return a value of 0. So we'll put that label over here. And all it needs to do is to load A with 0. And we're all done. If not, then I personally, I would do this, is to basically to remind myself, what does it mean if I did not take that branch to return 0? It means n does not equal to 0, okay? And immediately I put a jump around the return 0 block to return to caller, because this needs to be skipped around, because otherwise I would still end up returning a value of 0 even after all the hard work. So I need to jump around that to return to caller. Now I go back to backfill the code. To myself, okay, I cannot speak for you or anyone else, but to me, this really helps, because if I don't do this, I would typically forget the unconditional branch at the end. So it will kind of fall through to LDI A0. So no matter what you pass as n, it will still return a value of 0. Okay? Because that's one of my favorite mistakes to make, is to forgetting to close a block, to branch around a block that it's not supposed to go to. So I would do it in a structural way like this. Now, how you want to write your code is entirely up to you. All right, so now I feel really safe to kind of focus on this block of code, because what it needs to do in the outer context is taken care of already. So now I can focus on this expression here, which is calling SQR again with a value of n minus 1. This is why recursion is difficult for some people, because they overthink. Okay, some people overthink and say, but what are we going to do now? Because we are inside the subroutine square and we're supposed to call the subroutine square. What are we supposed to do? Okay, to quote Pinky and the Brain, Pinky is going to say, so Brain, what are we going to do now that we have to call a subroutine? Brain's answer is going to be the same thing that we do every time we call a subroutine, which is to push all the arguments, last argument first, push the return address, continue execution at the subroutine. When we come back, we clean up after the arguments. The same thing that we do every time. Okay? Because the most crucial thing that people do to not understand recursion is to overthink. I know because I did that. When I was an undergraduate student in a Pascal class, which is equivalent to your CISP 300/360, that was the one thing in my mind. It's like, how can this work? I'm in a subroutine and it's calling the same subroutine. How does that work? Turned out I was just totally overthinking about the whole thing. All right, so that means I have to push n minus 1. Well, I got n already in register C, so that makes it kind of easy. Decrement C. Okay, so now C has n minus 1. Got to push it on the stack. Decrement D, ST, D, C. So this ends up pushing n minus 1 on the stack. We all good. Now we just have to do the usual thing that we call, which is to push the return address, LDI A.5 plus, STDA. That's pushing the return address. And we can now continue execution at the subroutine that we are calling. The fact that it is the same subroutine that I'm in does not matter, okay? Doesn't matter at all. Then I clean up the stack after the subroutine returns. Okay, so let me just kind of pause here and see if there are any questions. Yep.
So for the decrement C,
let me turn on line number so I can actually oops. There you go.
On line 12, you say decrement C is, so C is equal to n minus 1. Wouldn't it be the address of
Nope.
n minus
Nope,
1?
because of line 7. Because of line 7, register C actually has n, not the address of n.
Got you.
Yep, because I did the dereference already.
Yes, yep.
Yep, because otherwise I cannot see whether n is 0 or not. So the fact that I could check whether n is 0 or not means that I got the value of the parameter already. Let me turn off my notification. I thought I got it programmed in, but apparently not. Okay. All right. So we still got a few things to do after it returns here, because now we have, so I'm going to remind myself what register A has. So register A now has the square of n minus 1, and I still got a few things to do, which is adding n twice to it and then subtracting 1 from it. All right, so question, okay, first question is, where can I find n? Is there a shortcut now? I mean, don't we still have n in register C? Okay, let me type it and then we'll answer the question. Is the value of n still in reg C? Question mark. There we go. That's what I'm asking. So now you have to go back to the contract between the caller and the callee. I'm not sure whether you guys still remember it, because it's important to understand the contract between the caller and the callee, because according to the contract, the caller cannot assume any registers to retain its original value after calling a subroutine. So that means register A, B, or C may not be the same as before the call. So that means I cannot count on register C still containing the value of n. Are we doing okay so far? Yep.
But isn't it still within the same call in this case?
Nope, because remember, okay, so remember what I said earlier, Pinky in the Brain, when you're calling a subroutine, so you can change what Pinky is asking Brain a little bit. So instead of asking, what are we gonna do, okay, when we call another subroutine, you can now ask, is this subroutine going to preserve the registers? And the brain is going to answer is like the same thing every subroutine does. Do not assume all the registers are preserved. It doesn't make a difference, okay? So that's the key is whether you're calling the same subroutine in a recursive call or whether you're calling an entirely different subroutine does not matter. Those contract still works. The caller cannot expect the callee to preserve the values of the registers. Is that okay? So that means I can't just go back and use C again. I have to kind of go through the whole calculation again. So now I have to say, okay, it's kind of a hassle because now we have to do another CPR, CD, okay, increment D, oops, C, and then we do SD, LD, CC. Now we get it back, okay, because there's no other way to do this. The only other way to do this is you push the value of register C on the stack first, and then you retrieve it from the stack later on, which is not much better than this approach. So I would say it's a draw. Possibly this is a little bit faster. Okay? So it's important to note why we cannot just say, hey, but we got N in register C already. No, we don't know for sure because we don't know what the subroutine is going to do. Okay, but now that we have it back, it's easy now because I can just say add that to A twice because we're supposed to add 2n to the return value of the square of n minus 1, and then we decrement a one time, and that's it. Are we doing okay so far? Any questions? No questions? All right. So let's check it out. Okay, let's find out whether this is going to do what it is supposed to do. Okay, this time I make sure I save first before I go back and submit the program. Okay, submit. This is called square. Okay, there we go. But before I press the enter key, let me give you guys one last chance to make a snapshot of the assembler because I'm about to change it. So can I submit now or are you guys still making a copy? You guys are good? Good? Okay, all right. All right, so we'll go ahead and submit and see if I made any stupid mistakes, careless mistakes. All right. So now we go into the trace, and if you are not patient and you go like, okay, let me check line by line whether the program worked or not. If you want to skip all the way to the end and see if register A has the value of 16, because 4 squared is 16, you can go to summary. It will give you the number of lines, in the trace, which is 204. You go back to the analysis tab and then just change the address of the cell that you're looking at to, I cannot remember what it was again. 204, okay, 204. So we can now go to C 204, press the enter key. All right, well, that's kind of close to the end. First of all, the stack pointer is balanced. That's always a good sign. And we want to find out whether the last time register A was updated, it got a value of 16, and the answer is yes, because this is in base 10, this is in base 16, so 1, 0 in base 16 is 1 of 16, and that's exactly the answer that I want. Is that okay? So this sample program illustrates quite a few important points. It illustrated all the things that we have learned already. Pushing the return address, popping the return address, okay? That's what we did from really early on. It also includes the illustration of how we push argument from the caller's perspective and how we access the parameter from the callee's perspective. But we did that also using the subtraction example. This one also illustrates how we convert a ternary expression into the control structure that we need, okay? Because the ternary expression just boils down to if then else, okay? That's basically what it boils down to. It also illustrates that we cannot trust a callee to preserve the registers. So you can either push the value of the register if it's really difficult to compute the same value again, push it on the stack, pop it later on. But if it's really easy to compute it again, it's okay. Recompute it instead. Is that okay? So let me ask you another question. How many bytes of the stack is actually needed for this program to work based on the square of 4? So how many locations of the stack ended up being used? So what you need to do now is to think about how many, how many bytes do we need to use per invocation of this particular subroutine. So per invocation, the first thing you need to push is n. The second thing you need to push is the return address. So we need 2 bytes per invocation. F of 4 has 5 invocations. Because f of 5, or square of 5, or square of 4, sorry, needs to compute square of 3, which then needs to compute square of 2, which then it needs to compute square of 1, which then needs to compute square of 0. So at the deepest portion of the recursive call, we have 5 levels of invocations. So as a result, it should consume 10 bytes on the stack, which also means if the first location that we can use is FF, the last location that we accessed in this case would be F6. Because F is 15, 15 minus 6 plus 1 is 10. All right? But how do we know that? Okay, this is also why the trace is useful, because if I go back to the trace, I can focus on column C, and then we can identify where did we, what is the lowest location in RAM in the stack that we modified. So if you go back up, you can see the last update is at location F6. So this is how I know up to 10 bytes were in use in the stack when I executed this program. Are there any other questions about this particular program? I will make a snapshot, okay? So I'm gonna ask you guys again, you don't have to answer, but this is just me prompting you to think about it, is how do we study for this class at this point? The rules are very simple, but it doesn't mean that you just read the rules and then everything just kind of sinks in and you're ready for the final exam. So how do you study for this class at this point?
Write code.
You can write some code. You can basically give yourself some additional assignments, programming assignments. Yep, you can do that. But even given the sample programs that I have written, I would go to the source of each one of each program that I have written and really kind of comment on every single line of what it is doing and also why it's doing it, making the connection all the way from what the instruction is actually doing to the context in C and C++. Making that entire connection is going to help you truly understand what we are doing here, and that will be very helpful in the final exam. So I'll give you an example. I'm just going to randomly pick a particular instruction, which is, oh, I cannot decide. I'll pick this one here. What is this? Okay, the what is easy because you look up the opcode table and it will tell you, oh, we are adding the value of register C to the value of register A and then store the result in register A. That's really easy, but that's not going to be helpful, okay? Because what we need to know is, but why are we doing this? This is a part of what in the C++ program, okay? Oh, this is a part of the recursive call because we have to add n to the whole expression twice. And n is in register C right now, and a is the summation of all the different terms, and that's why we're adding C or n to a. Okay? So now the follow-up question is, how do we know register C has the value of n? Well, that's because we got these 3 instructions. Okay, so what do they do? What do they do? We copy register D to register C. That's the what. But why are we doing it? Because we are not supposed to modify the stack pointer. But yet, what we need to access, which is parameter n, is living on the stack. So to get there, I need a different register to play with to get to that point, to get to that address. That is why we have a CPRCD. What is this? Increment C. Easy answer. We are adding 1 to register C. Totally useless answer, because we also need to ask, why are we doing this? Because of the way things are pushed on the stack. The argument is pushed first, the return address is pushed last, and as a result, the argument is living 1 byte above the return address. So by incrementing C, which was pointing to the return address, it is now pointing to the parameter that we need to access. Okay, what is this LDCC? We are using register C as a pointer. Go to that location in RAM, retrieve the content, and then use it to overwrite register C itself. That's the what. Okay, what is the instruction doing? Which is useful, but in the context of the entire thing, that's not the only question you need to ask, because you also need to ask, why are we doing this? Because register C at this point only has the address of the parameter, but I need to get to the value of the parameter. So that's why we need to use an LDCC. So all of those are the steps that I want you guys to be able to practice, is to look at every single instruction, ask those questions, make the connection all the way from what the instruction is actually doing at the lowest level to how it relates to back to the C code. So the C code here is this part here. Are we good so far with all of this? Okay. Let's see. What else? What other fun things can we do?
I tried writing a program to check if a number is even or not.
Mm-hmm.
Was that something that we've done before, or?
You could do that. Um, okay, so I would suggest making it a little bit more generalized. So you want to see if a number is wholly divisible by another integer. How about that? Because in that case, you need 2 parameters, and that will make you practice which one am I supposed to push first. And also, when you access it as a parameter from the callee, you have to now think about, where is this thing here? I know one of them is right after the return address, but which one is right after the return address? So I think if you have 2 parameters, it will prompt you to answer those questions, and that will give you a better understanding of the material. But other than that, there's no mod operator. So checking whether something is divisible by 2 is very easy, because you can use a masking technique using AND. You can mask the rest of the bits except for bit 0, and then that can tell you whether it's even or odd. But if you give it a general integer, then it becomes a little bit harder. You need to use a loop to do quote-unquote division. But that would be a good exercise, okay? Using a loop, how do we write that loop? How do we, okay, so do you want me to kind of give you the code, or do you want to figure it out?
The even one was more for me, like trying to like work functions. This is me trying to figure out how like functions work.
In that case, yeah, work on that one first, and then work on the one that is more generalized, which is to ask, is this number a multiple of this factor? Do you guys want me to give you the kind of a ungraded assignment, so you can kind of work on it? I see some shrugs like maybe. Okay. All right, I'll give you that. So divisible. There we go. But I will only give you the C code version, standard integer.h. So it's going to return 0 for not divisible and non-zero for divisible. So int divisible uint 8_t and uint 8_tf. So we can assume f is non-zero. Okay, so that's an assumption you can make when you write this code here. So the idea is to say while n is greater than or equal to f, do the following, which is n minus equal f. And what you're returning in the end is to check whether n is greater than 0 or not. But you have to negate that. Okay, fine. We'll do it like this. There we go. All right, so this is divisible. You need to call divisible from main. So you can call divisible, give it one case where it is divisible, and one case is not divisible, and in one case where it has to go through at least one iteration of the loop, in one case that it does not need to go through one iteration of the loop. So you can say, I want to check if 1 is a multiple of 3. Okay, the answer should come back as a 0, which means it is false. Divisible 5, 3. This should also come back as a false. Divisible, 0, 3 should come back as a yes. 0 is a multiple of 3 because 0 is 0 times 3. Okay? And then we have divisible 6, 3 should also come back as a yes. And return 0. So these are test cases, okay? However you want to code your program to test for these test cases, it's up to you. But the key is divisible itself. How do you write it? We have all the tools, okay? We have talked about all the tools to do this already. It's a matter of translating the C code into assembly code to get this done. All right. Just looking at the time here. So I can give you a preview of what we'll be talking about next Tuesday because Thursday is a holiday. So I won't see you guys for an entire week. And that's why it is super important for all of you to kind of keep the quote unquote keep the engine warm because otherwise we come back on Tuesday and we go like, I have no idea what parameters are or how to do the arguments and so on. That would not be good, okay? Because on next week, okay, I think that's the last week of class or second to the last week of class. Second to the last, I think, ish. We have 1 week and a half or so after Thanksgiving. Is that right? Because I think the final exam schedule starts on the 12th. So that doesn't give us a lot of time. Anyway, starting next Tuesday, we'll be working with arguments, and then we'll move on to structures. So structures are not super difficult concepts, but it does require you to have a good understanding of how things are organized. So, and also a competency of understanding the instructions. In other words, okay, let me give you an example of what I mean by competency with the instructions. So if I look at sqr.ttpasm, if I look at this program and I look at some instructions here and I go like, I don't know what that instruction does, that would be alarming. Okay, if I pick one particular instruction and say, I don't know the difference between an LD instruction versus an SD instruction, that would be very alarming. Or I cannot differentiate what is LD versus LDI, that would be very, very concerning. So understanding what each instruction does is really the super low baseline at this point of this class. Now, do you have to understand how it is being done inside the processor? The answer is no, okay? I can tell you that I'm not going to structure the questions for the final exam around, okay, do you know how this pathway is done? Which multiplexer is turned this way and which demultiplexer is turned the other way? No, that is not needed anymore. But do I need you to understand what each instruction actually does? Yes, that is still very, very important. Okay, so I do want to make sure that you understand in this context, in the context of what we're doing now, what is important, what is not so important. Any questions before I move on and potentially use string length as an example? Yes.
What is LDI a .5 plus? I don't know what that.
Okay, that's a very general question. So are you asking about the .5 plus?
Yeah, .5 plus.
So the dot is referring to the address of the instruction of the same line. That was
5 plus is just.
is a postfix notation for adding 5. Okay, so you might, okay, so there are two suggestions. One is you might have missed the beginning of this class. So that means reviewing the video can be helpful. Second one is we talked about postfix notation. This is in what we call a postfix notation. I think there's a module in Canvas on postfix notation, so I would definitely read that one too.
I think it's also in the assembler manual where there's like a full
Yep.
explanation of the postfix.
Yep. Very good. So let me point out where to find that document, because it is sometimes I kind of rely on people to read the document just because it is there, but that's based on an assumption of how I would take a class, which is not always a good model.
How do you keep all those tabs straight? How do you keep all the tabs straight?
I got two tools that is really helpful. One is a vertical tree tab, so it's easy to read actually what is on the tab. The second one is a search bar. Oh, you guys cannot see it. This one is a little tricky because the moment I click on it, it disappears. Anyway, it pops up a little dialog box, so I can type the keyword that I'm searching for, and it will locate the tab and move to that tab for me.
I do like the vertical tree one. I might get an extension for that one.
Yeah, when you have like 30 tabs per window and then about 3 or 4 windows, because I do coding also. When I learn a new programming language, I cannot remember things, okay? So what is the method that allows me to do blah, blah, blah? I know there's one, I just cannot remember the name of the method and also the ordering of the parameters. So I always have to look things up, constantly. All right, so what you're referring to is the assembler manual. And if you have not read it, I would recommend you to take a look at it. Not the entire thing, because some portions of this is not really relevant, but it does talk about the postfix notation right here. It talks about the instructions. It talks about the basic architecture. It talks about how to do the assembling, how to debug. The implementation is not needed, okay? So you don't need to go as far as the implementation, because that really goes to the details of how the assembler itself works. Now, after this class, over the winter break, for those of you who feel absolutely bored and you have absolutely nothing else to do, yeah, go for it. How can you turn the spreadsheet into an assembler? Yeah, go ahead. Knock yourself out. This is all open source. So, getting back to string length, right? Okay. So string length, I haven't really talked about local variables yet. So the question is, how can you implement string length without using local variables? Okay, so let me just check with the whole class. Does everybody understand what is string length? strlen as a function. It returns the length of a null terminated string. So we are good? Okay, all right. So typically what people do is to implement string length, okay? So I can give you string length.c, and I'll just do the quick and easy version here, okay? So we have string length const char point to ptr, and it's supposed to return the length of the string that the pointer is pointing to. So typically you need a local variable to keep track of the counting, right? Or you can keep track of a pointer, okay? So you can return the difference between the original pointer and the eventual pointer pointing to the null character. You can do pointer arithmetics, in other words. So you can do all that, okay? But you still need a local variable to do that. And I haven't talked about local variables yet in this class. So how do you do all this without using a local variable? So brain, how do we do this? The same thing that we do with every problem, recursively. Mm-hmm. I can see memes now, popping in my head, like Pinky and the Brain, just asking those questions, and brain keeps answering the same question the same way. It's like the same thing, the same way that we do everything, recursively. Okay, so these 5 minutes will give you hopefully, some insight of how to uh, code recursively. Think of the base case first, the simplest case, okay? What is the easiest thing to do when it comes to measuring the length of a string? Oh, this pointer points to a null character. The length is 0. Does that make sense? That's the simplest case, okay? There's nothing else to do. You gave me an empty string, and I'm going to give you an answer of 0. Okay, so that means you say, is it pointing to something that is a 0? If that is the case, the length is just 0. Okay, that's the base case. So now the question is, what if I'm pointing to something that is not null? How do I transform the original problem into one little step that I need to do plus a subproblem that resembles the original problem? So in this case, it becomes 1 plus. The 1 is the character, the non-null character that I see. And then I transform the problem to a subproblem, which is exactly the same thing, which is what is the length of the remaining portion of this entire thing? I took care of the first character, which is non-null. That's the 1. What is the length of the rest of the string? So now you call string length again, but for the rest of the string. So now I have no local variables, but I'll be able to figure out the length of a string. Hmm?
This kind of goes until it hits the null character.
Hmm?
This goes until it hits the null character in the string.
Yep. Go ahead.
A string is it's an array of characters, right?
Yes.
So you've got the null terminator, and then from there you can keep on looping it until you reach the null terminator.
It's kind of the other way around. So the counting does not happen until we start to return. So let's just say that we have a string that has 3 characters followed by a null terminator. Okay? So it's TAK and then a null terminator. Okay, just as an example. And I'm the first, invocation of string length. So when I'm given the pointer, it's pointing to uppercase T as a character. So I go like, okay, I see uppercase T, which is not a null character. So according to this code, I'm just going to say, okay, it is 1 plus, okay? The 1 is the character that I saw. And then I say, but I don't want to work on the rest of the string, okay? I'm too lazy to work on it. Why don't you work on it? Okay, so I gave you a string, but it's a substring, and that's what PTR plus 1 is about. It is the rest of the string that I'm supposed to process. So you get a substring, which is AK, and then a null terminator. You saw ASCII code, the ASCII code of A, which is non-zero. You go like, okay, I see at least 1 character, but I don't want to deal with the rest. So you gave him the substring, which is K followed by a null terminator. You saw the K, you say, well, it's not a null term, it's not an empty string. I took care of 1 character, I don't want to take care of the rest. And then you finally gave him the pointer that points to the null character. So you got an easy job. You go like, oh, I only see the null terminator. The string is empty. So I'm going to return a 0 back to him. So you say, okay, the rest of the string has a length of 0. I see 1. So I'm going to return 1 plus 0, which is 1 to him. And then he returns 1 plus 1 to me, which is 2. And then I look at the 2. I go like, okay, I saw the t. The rest of the string has a length of 2. So combined with the t that I saw, the length has 3 characters. So I just return 3 to whoever called me in the first place. Is that okay? So it is a way of looking at things. Just like object-oriented programming is a way of looking at things. Yes, we do have object-oriented programming languages, like C++, Java, most programming languages are object-oriented these days. But it doesn't mean that you cannot perform object-oriented programming without a programming language that supports object-oriented programming. I can do object-oriented programming in assembly language because it's basically a way of looking at things, a way of thinking of how to divide a problem, and how to you reuse code as much as possible. So I can write your object-oriented programming code in assembly, even though the language has absolutely no understanding of classes and methods and abstract methods and all that fun stuff. But it's about a way of looking at things that matters. So this part is not related to assembly language programming. It is actually about general programming. But I think it illustrates that the approach or how we look at things is far more important than the language itself, which is just limiting how we can express things. All right, so we are right on time today. I will go ahead and release the lab of today, and so you guys can work on it. But I would say, if anyone needs additional explanation or a discussion, just come to my office hour, which is right before this class. I try to make my office hour as convenient as possible to most people. So, all right, so I lost track of my Canvas. See how useful it is? It points me right back to where I need to find it. All right, so the lab of today is parameters and return value. Let me go ahead and release it. And I will show you the correct answers by 12 p.m. The access code is FRAME, F-R-A-M-E. You might want to write it down right here. And I'll give you until noon time to turn in. My other class on Monday, got it done pretty quickly, so I don't think it's going to take you guys that much time. All right, so if you refresh, you should be able to see the lab activity for today. And I'll go ahead and stop the recording.